Hello, I'm Tim, and today I'm going to talk about series and their applications in daily life. So first of all, we need to find what a series actually is. So it is simply just a collection of numbers which you add together. And these come in two types, either finite or infinite. We're going to look at the finite case to start with. And for our purposes, we're always going to start the sum at 1. So we have f of 1 plus f2 plus f3, and we do this all the way up to f of n, and we write this in the following way. We say it's the sum from k equals 1 to n of fk. Now, since this is a finite collection of numbers, we know that when we add them together, this will equal some number. We'll call it capital N. And for a finite series, finding this value, capital N, is the main thing that we're interested in. We're now going to look at an example. Say I wanted to add the numbers from 1 up to 100. How can I do this? Well, I can do it in the following way. I compare numbers together such that they add to make 100. So I have this 1 and 99, 2, 98, and so on. And I'm going to be left then with a number that's 100 and also this 50. So then I get 50 times 100 plus an additional 50, which gets me 5,050. Okay, so now what about the general case, where instead of summing from 1 to 100, I'm just summing up to any n. Let's try and use the previous example, though, to help us. So how many pairs of numbers did I have that added to make 100? There was 50. So here, that will be n over 2. And remember that I added to make 100, so I'm going to need to times this by n. And recall that we also had a 50 left over. So in this case, will be n plus 2. When we rearrange this, we see that it's n plus 1 over 2. And that is our general formula. Okay, so let's discuss a couple of applications of finite series. The first of which is approximations. So this is where if you had something very difficult to compute directly, you can instead approximate it by using a finite series. And as we discussed at the beginning, we know that this finite series will have some value. The second is permutations. Now these are defined directly using finite series, and they appear in the areas of probability and statistics. And finally, they're just used in any area of mathematics to do general computations, and are heavily used in the areas of finance. We're now going to look at the infinite case. So here, instead of going from 1 to n, I replace n with infinity. So I have that it's the sum from k equals 1 up to infinity of f of k, which is equal to f of 1 plus f of 2, and it keeps going on forever. So here, these are slightly more interesting because we don't know what this is equal to. There's no reason why if I add an infinite number of numbers together, I should get something finite. But if I do, again, I call it capital N, and I say that the series converges. So why are we interested in infinite series? Well, one reason is that we can write certain functions in terms of them. So here we have e to the x, which is one of the most commonly used functions in the world. We can actually show that it's equal to the infinite series of x to the n over n factorial. So if we were to write this out, that would be 1 plus x squared over 2 plus x cubed over 6, and so on. Now, if we go back to the finite series case, we said that we could just use approximations to get values for something. So here we could use just the first 4 terms to get an approximate value. And as we said in applications, that is often good enough. To finish with, I just want to look at one example of a function which is defined in terms of an infinite series. This is the so-called Riemann zeta function, where here we have it's the infinite series of 1 over n to the s, where s is the variable. So if we looked at an example, this would be zeta of 2 would be equal to the infinite series of 1 over n squared. And if we work out the first couple of terms, that's 1 plus a quarter plus a ninth, and so on. And we can actually show that this is equal to pi squared over 6. Now this is quite remarkable because all of these numbers here are rational numbers, but this is an irrational. This function has a lot of interesting properties. Many people have spent time looking into them. There's also the Riemann hypothesis. This was stated by Riemann himself in the 1850s and is considered one of the hardest problems in mathematics. It basically says when this function zeta of s is equal to 0. But why should we care about the Riemann hypothesis? Well, first of all, because of the complexity of the problem and how long it has been unsolved. If someone did eventually solve it, they would receive $1 million. But for more mathematical reasons, this function is heavily related to prime numbers, and prime numbers form the basis of cryptography. And cryptography is used everywhere in the world today, from emails to internet banking to remote control vehicles. It also appears in mathematical physics, dynamical systems, and probability theory, all of which give models to the world around us, such as the weather, the atmosphere, and also waves. We hope that you have found this video interesting and have learnt something about series and their applications in life. Thank you for watching.